Our next speaker is Dr. Filippo Costantini. He's the Marie Curie Postdoctoral Fellow at McMaster University in the Department of Philosophy and at Foscari University of Venice. His interests are in philosophy and mathematics, logic, and he's currently working on a project on the philosophy of mathematics of G.W. Leibniz. We were trying to identify, an interesting fact about Filippo outside the lab, and apparently he has no other interests. Even in his spare time, he's thinking about math. Over to you, Filippo.
Thanks, Joe. Thanks very much. So I'm going to expose some philosophical thoughts about mathematics. So people tend to think of mathematics as an objective science, which would describe a reality totally independent from us. And the work of the mathematician is usually seen as a work of discovering such a reality. Moreover, mathematical knowledge is seen as a process of accumulation of new and new results. Tonight, I'd like to challenge this view. And to do that, I'm going to focus on a very specific case, namely the case of the infinite. So, have you ever counted to infinity? To understand what it means to count to infinity, we must understand how we can compare different infinite collections of objects with regard to their size. So let's consider the sequence of numbers, 1, 2, 3, and so on, and the sequence of even numbers, 2, 4, 6. So one first idea would just consist in noticing that the second sequence is a part of the first one. So the even numbers are a part of all numbers. And this suggests that the even numbers are less than all numbers. However, there is another very intuitive idea, and this is the fact that we compare each element from the first sequence with exactly one element of the second sequence. So it is just enough that we pick up a number from the first sequence and we pair it with its double. So we pair 1 with 2, 2 with 4, 3 with 6, and so on. And what this suggests is that the even numbers are as many as all numbers. So we are facing a paradox here because we have two different arguments. According to the first one, the even numbers are less than all numbers, while this is not the case according to the second one, because the second one shows us that the even numbers are as many as all numbers. So how can we avoid such a paradox? So more or less 250 years ago, Leibniz, a German mathematician and philosopher, proposed a way out of this situation. And he considered the fact that we compare the numbers with the even numbers as showing that a part of the sequence of number is equal to the whole sequence. So we have as many even numbers as numbers. And he believed that this fact is impossible because this goes against one key idea, which is the idea that the whole is always bigger than its parts, which was an idea that at that time most of mathematicians believed to be an obvious mathematical truth. So his conclusion is that there cannot be a real comparison between infinite sequences, essentially because they are infinite. However intuitive this idea may sound, more or less one century and a half after Leibniz, another German mathematician, Georg Cantor, gave a totally different solution to the same problem. So again, Cantor started with the pairing between the numbers and even numbers, and he suggested that we should simply accept as a fact that a part of the sequence of numbers is equal to the whole sequence. But to do that, we must reject the idea that the whole is always bigger than its part. So Cantor's solution is essentially based on this rejection. And on this basis, it could develop a theory, a very interesting theory of infinite collections, where we have infinitely many infinite collections, and some of them are bigger than others. So in a way, we have infinities bigger than other infinities, which is, bigger than other infinities, which is, I think, quite counterintuitive, but that's the theory. And this theory became standard in mathematics. So if you speak with a mathematician nowadays about the notion of infinite, he will have in mind for sure Cantor theory. While Leibniz's view on this topic essentially got forgotten. So you may wonder whether it still makes sense to study Leibniz's view on this topic again. And I do really hope it makes sense because it's what I'm doing at the moment. But here the key fact to understand is that there is no logical mistake in Leibniz's solution, in the precise sense that given his premises, his conclusion follows. So the disagreement between Leibniz and Cantor was a disagreement at a deeper level. They disagree about the very same concept of number. According to Leibniz, the concept of number must respect the idea that the whole is always bigger than its parts, while this is not the case for Cantor. So with all of this in mind, we can go back to our original question: is mathematics an objective science? I presented to you a paradox and two solutions. Both solutions are legitimate in the sense that, given their premises, their conclusion follows, but they are incompatible with one another. So if you accept one solution, you cannot accept also the other. So what this situation shows is that there is no objective reason to think that one solution is true while the other is false. We may have reason to prefer the Cantorian view on this topic, maybe because his theory is more powerful, is more fruitful, but these are not reason to think that Leibniz theory is false. Moreover, Cantor's solution essentially consists in modifying the definition of number that mathematicians had accepted until his time. And this modification is accomplished by rejecting the idea that the whole is always bigger than its parts. So there is a sense in which his theory depends on the way he characterized the concept of number. So if we put together these 2 points, I think we get a quite determined answer to our question. So is mathematics an objective science? Well, only in part, because it allows for deep disagreement between mathematicians, but also it allows for alternative but still legitimate mathematical theories. Thanks very much.
Thank you so much for sharing your work. As someone who wanted to be a mathematician when I was a child, I find this incredibly fascinating. And so I think maybe all of us were kids at one point and tried to count to infinity. So we have a question that sort of links that. What made you want to study such a niche topic like the philosophy of mathematics?
Oh, well, that's interesting. Essentially because as an undergraduate, I liked both philosophy and mathematics. And what I liked most were like logical paradoxes. And I discovered that essentially philosophy of mathematics is all based on some different paradoxes, and you try to solve them. And you see that actually when you have a paradox, so a situation that it seems like impossible, that you don't know how to solve, then this trigger, it usually triggered a new development. So I was really interested like in paradoxes essentially. And that's the reason why I decided to work on philosophy of mathematics.
Fantastic. Thank you so much. I think it's just so abstract to what we all know. So it's, opening up a whole new world for us. Is understanding infinity a problem that can be, quote, solved by artificial intelligence?
Oh, that's very interesting. So as I see it, artificial intelligence is very useful when it comes to computation. But the problem that I'm not an expert of artificial intelligence, but the problem that that I see when it comes to the notion of infinity in mathematics is that this notion requires a lot of non-constructive reasoning, and non-constructive is a technical term, but just to give you an example, essentially a non-constructive proof is like a proof where you show that there must be a mathematical object which has a certain property, but you are not able to show an example because you don't have like a mechanical procedure, an algorithm that allow you to compute that number, that object. So I think that maybe this is a problem when it comes to artificial intelligence, maybe a limit when it comes to the notion of infinite. Yeah, so, but I mean, it's just a guess. So I mean, let's see what the future will bring us.
Fantastic. Thank you so much, Filippo. I think, again, yeah, you're expanding people's minds with things that they just haven't ever thought of before. So it's really interesting. Thank you.